All right, these are your 7-5 exponential function notes. In this lesson, we're going to learn how to graph exponential functions. We're going to find the y-intercepts of these graphs, and we're going to be able to identify the domain and range of the function. We're also going to be able to determine whether or not data represents exponential behavior based on a table of values. So lots of exponential functions. We did the activity before break involving exponential growth and decay. And so now we're going to put it to use in the formal sense. So an exponential function is a function where the variable, the unknown value, is the exponent again. And then we look at what happens when you graph that. So it's an exponential equation, but now we're going to graph it. Y equals that exponent. So y equals a times b to the x is the format. Now, why do they keep that a and b separate? It's really important to understand that we write it this way because we are not raising a times b to the x power. We want to make sure that you understand if I have y equals 2 times 3 to the x, 3 is being raised to some power, and then we multiply by 2. So it's really important that you understand that. A cannot equal 0. If the a value was 0, in this same example, you'd raise 3 to some power, get a number, and then times it by 0, and you get 0. You would get 0 every single time, and that's boring. It would just be a constant line at 0. It would be a horizontal line. So that's not exponential growth or decay. The b value cannot equal 1. That's boring. Let me show you. If you had y is equal to 2 times 1 to the x, well, 1 to the second power is 1 times 1, which is 1. Times it by 2, you get 2. If x was 5, we'd multiply 1 times 1 times 1 times 1 times 1, which is 1, times it by 2, and you get 2. So everything would be just 2 every single time. Boring. Not an exponential function. So those are some things that have to happen in order for this growth or decay to occur. So a cannot equal 0, b cannot equal 1, and b has to be positive. Otherwise, you're going to be going back and forth between positive and negatives, and your graph's going to get all funky. So it's either got to be a positive b value. If b is bigger than 1, it's called exponential growth. If the b value is a proper fraction between 0 and 1, so 1/2, 3/4, 0.5, 0.2, anything that is less than 1 but still positive, we consider that exponential decay. So when we do this, you just make a table of values to graph the function and you plot them. You won't have a ton of points to plot. You're going to use more patterns. So looking at number one, my a value here is 1. There's a 1 out in front here that's just understood. My b value is 2. And so number 1, because b is greater than 1, this represents growth. For number 2, my a value is 3. My b value is 0.4, and because 0.4 is between 0 and 1, this would represent decay. And the third equation here, my a value is a -1. There's a -1 out in front there. My b value is 2.3. Now, because 2.3, even though it's a decimal or a fraction or whatever it is, it's still greater than 1, so it still represents growth. All right, so we're going to get right into the graphing part of this. We're going to graph these. We're going to find where it crosses the y-axis. We're going to identify the domain and range, and then we're going to determine if it's growth or decay. Actually, we can determine growth or decay right from the beginning because it doesn't have to do with the graph. It has to do with the b value. And just to recall, domain are your x values of a function, and your range are your y values. All the x values that belong on this graph and all of the y values. So it's going to be a little different. We haven't done domain and range in this sense in a long time. It's not limited to just the values in the table. So we'll talk about that. So first of all, let's actually do the growth or decay part. Because my b value is 3, that's greater than 1. So this is going to represent a growth, exponential growth. Okay? So we're just going to plug in points for the x value. We can use our calculator to figure it out. And then we're just going to plot those points. So I'm going to kind of plot as I go. So I'm going to plug in x is 0. Now, if you recall way back in first semester, we learned that your y-intercept is found when x is 0. So this is also going to give us our y-intercept. When x is 0, you don't shift to the left any, you don't shift to the right any, and so you're on the y-axis. When you plug 0 in for the exponent, you get 3 to the 0 power, y is equal to 1. So 0, 1 is my y-intercept. Okay? Anything raised to the 0 power is 1. So my y-intercept is 1. And I can label that right here. This is my y-intercept. And then I'm just going to pick values that make sense. So I'm going to use 1. I want to plug in 1. So when I plug 1 into this equation, I get y is equal to 3 to the first power, which is 3. So I'm going to plot that ordered pair, 1, 3. Over 1, up 3. And then I'm going to plug in 2. And when I plug in 2, I get y is equal to 3 squared, which is 9. So 2, 9 is on my graph. And what you're realizing is each number I go, now 9 is going to be way up here in my words. If I go any higher, I'm going to run out of room. For instance, if I do 3, that's y is equal to 3 cubed. That's 27. I don't expect it to do that. So I think we're good from this point on. So from my y-intercept up, I can kind of create a pattern. It's a curve. Okay, it's not a straight line. But now we got to figure out what happens to the negative values. What happens when I plug in a negative value? What's going on the other side of my graph? So let's go ahead and plug in a negative 1. When I plug in negative 1, I get y is equal to 3 to the negative 1 power. Well, 3 to the negative 1 power flips my 3 and makes it y equal 1/3, or 1 to the 3 to the first, which is 1/3. And on a graph, that's about 0.3 repeating, right? 0.3-ish. So at negative 1, we're going to be at 0.3. If I plug in negative 2, I'm at 1/9. So I'm just going to extend my table here, erase some of my work. And what you're going to find out in exponential growth and decay, when I plug in negative 3, I'm going to get 1/27. Really, really small, really close to 0, but not really equaling 0. And notice all my y values are still positive. If I fast forward, to negative 100, okay, let's just pretend I went way over 100 units to the left. When I plug that into my equation, I get 3 to the negative 100 power, which flips it and it does 1/3 to the 100th. That is a really small number. If you use your calculator, 3 to the 100th power is extremely small, and it's still positive. And so what happens is we end up with a graph that wants to go, but it never crosses. It goes towards the x-axis, but never crosses the x-axis. And so we call that line, we'd call that an asymptote. And we'll talk more about that in Algebra 2. But it's a line that the graph approaches but doesn't cross. Okay, this graph will never cross over that x-axis. Unless we did some things to this graph, it's never going to go into the negatives. Okay, so now when I go to answer the domain and range question, I am not just asking for the values that we put in our table of values. Those guided us. But when I connected those dots, I said every fraction, every decimal in between is included on this graph. So what I need you to do for domain and range, I want you to look at this in terms, if you move to the left and to the right on this graph, all along the x-axis, okay? As I'm looking, I'm just looking here. I'm marking it because you can't see that I'm looking. As I move to the left and to the right, every single value hits the graph. If I'm at 6, if I went way up forever and ever, I would hit the graph. And if I'm at -6, I would hit the graph. And if I'm at 0, I'm hitting the graph. Every number on the x-axis is on this graph. If I went way over to the right to 1,000,000, I would hit this graph if I went up. And if I went way to the left to -1,000,000, I would still be hitting this graph. There's no holes, it's all there. So my domain is all reals. I want you to understand that means every x value on the coordinate system will find a place. I could pick any x and plug it in here. My range, though, I need to look not to the left and to the right, but now I need to scan my eyes going up and down. So I'm going to scan this graphing area, and where am I hitting the graph? Well, my graph only occurs from the x-axis up. There is no graph down in this region down here. There's absolutely no graph down here. So these negative numbers of y are not part of this function. So the values of this function that work are from 0 on up. All of those numbers are there. So what we say is the range of values on this graph are y greater than 0. Doesn't really equal 0. Remember, these numbers kept approaching 0 but never reached it. Never went negative. Okay? So I know that's weird, but as we do these, I think you'll get a little bit better at them. Let's look at the next problem. All right, so now this one has a base that's less than 1. So because my base is 3/4, I have decay. So this represents decay, okay, because of this 3/4 base. Don't look at the A value, just look at the base. So I have that part finished. Let's go ahead and make a table of values again. And I really think it's to your benefit to pick values that are negatives to make the small number bigger, but it doesn't matter. We can use both positive and negative values. So let's go ahead and plug in 0 to find my y-intercept. Your y-intercept is when x is equal to 0. My y-intercept here, when I plug in 0, I get y is equal to 3 times 3/4 to the 0 power. 3/4 to the 0 power becomes a 1. Anything raised to the 0 power becomes 1. And so I get 3 times 1, which is 3. So in this case, my y-intercept is 3. When I plug in 1, and I get y is equal to 3 times 3/4 to the first power. And 3 times 3/4 is 2.25. So we're just going to guesstimate 2.25. So I went over 1, and I'm going to be up 2 1/4. Let's plug in 2. When I plug in 2, I get y is equal to 3 times 3/4 squared. You can type that into your calculator. Just make sure that you square the 3/4 first, which gives you 9/16, and then times that by 3, 1.6 or 1.7-ish, 1.6875, so 1.7-ish. So at 2, I was at 1.7. And I'm approaching, but I'm not quite getting there really fast. So maybe I'll plug in 4 next, see what happens at 4. When I plug in 4, y is equal to 3 times 3/4 to the 4th power. So I'm going to take 3/4 to the 4th power first, then times it by 3, and I get 0.9, 0.94, 0.95. 0.9. So you just keep plugging in values just below 1. Let's go ahead and flash forward. I feel like I'm approaching that 0 again. Maybe not as fast, but I'm approaching that 0 line again. So let's fast forward and let's plug in 100. Let's see what happens when I approach 100. So I'm going to take 0.75 to the 100th power, and then I'm going to times it by 3. And I do get some scientific exponential number. I get a really, really small number. I get 9.6, and my calculator says times 10 to the -13th power, which means move my decimal 13 places this way. It's a really small positive number. So I know I'm approaching the x-axis yet again. When I plug in -1, my numbers are going to go up higher. So when I plug in -1, 3/4 to the -1 power will flip it and make it 4/3. Times it by 3, and you end up getting 4. So, oops, I'm sorry. -1 gives us 4. And so now we know that we're approaching this direction, going up, and then we're approaching, and we're not going to go across that x-axis. You will not cross the x-axis on any of the graphs that I give you. In Algebra 2, we'll talk about those type of graphs. But so once you establish the pattern, you can know that you're always going to approach the x-axis but never cross it. The rest of these numbers, you just have to use a few numbers to establish a pattern and then create your curve. Now, when we look at domain and range, okay, domain, I'm going to move this line and see, will this line hit the graph as I go over here to the left and to the right? So my domain, this is what my eyes are doing. If I'm way over here, I will hit the graph way up top. If I'm over here, I'm still hitting the graph, I'm on it. As I go to positive 100, positive 1,000,000, all the way to -1,000,000, I will hit that graph somewhere. So once again, my domain for this graph is all reals. And you're going to find that that happens all the time for these graphs. Now, if I take my eyes now and look at the y-axis, up and down, as my eyes scan this graph up and down, they're hitting the graph everywhere from 0 on up. There's no graph down here. And so my range is from 0 on up. And how you say that mathematically is we say the range are the y values that are greater than 0. So that's the other pattern you're going to find, is that your range is going to be greater than 0 or less than 0, depending on, are you above the x-axis or are you below the x-axis? In these last two examples, our range was above the x-axis. In this next example, it's going to fall below. So this last example, we have y is equal to -2 times 2 to the x. Maybe you can make the connection as to why the graph falls below the x-axis this time. Maybe use some of your other graphing techniques. When did the line switch? When did the line rise to the right versus falling to the right? It has to do with the slope. Well, your a value sort of serves at that same purpose. This -2 is going to make my graph fall. It's going to go underneath the x-axis. It's going to be upside down, okay? So we still, though, look at the base value, the b value for growth or decay. So even though it's going to end up going below the x-axis, because this is a 2, it's still growth. It still represents exponential growth. And we can go ahead and just plug in our points. So I'm going to use 0 for my y-intercept. When I plug in 0, I get y is equal to -2 times 2 to the 0, which 2 to the 0 becomes 1. And so y is equal to -2. So my y-intercept is 0, -2. And I'm wondering if you're making any connections there that your a value ends up being your y-intercept. You're going to have 1. Sorry about that. I had a little interruption. We're going to plug in 1 now. And so when we plug in 1, we get y is equal to -2 times 2 to the first. And that's really -2 times 2. So your y value would be -4. And I'm going to plot that as well. So 1 gives me -4. When I plug in 2, using my calculator or just showing my work, -2 times 2 squared, that's -2 times 4, which is -8. So the numbers are increasing in a negative fashion. They're getting bigger, which is really they're getting smaller because they're going in the negative direction. 2 to the -8 is way down here. It's actually off my graph. And then let's go ahead and plug in some negative numbers. So if I plug in -1, when I plug in a -1, you get y is equal to -2 times 2 to the -1. 2 to the negative 1 flips it and makes it 1/2. And so negative 2 times 1/2 makes negative 1. So when I plug in negative 1, 2 raised to the negative 1 power is 1/2. Times that by negative 2, and you end up with negative 1. So negative 1 gives us negative 1. And when we plug in negative 2, 2 to the negative second power, you can use your calculator, is a quarter. And then times that by negative 2, and you're going to get negative 1/2. So just trust my math there. I'm using a calculator, negative 2 and 1/2. What's going to happen is we're approaching the x-axis again from the negative sense. It will never cross. So I know it levels out over here. I've established a pattern, and then it's falling in a curve. Okay, so there's your graph. You got your y-intercept. Let's look at our domain and range. When I look at my domain, I'm scanning the graph from left to right. I'm hitting the graph over here. If I continue this graph all the way over here, I'd still be hitting that arrow. Okay, and then way over here, I have to go really far down, but I'd still hit it. So when I scan the graph from left to right, those are your domain values. Notice I'm crossing I'm scanning the x-axis. My eyes are scanning the x-axis. I'm hitting all of them. My domain for this graph, again, is all reals. Every x value is included on this curve. When I scan this curve for my y values, when I scan the y values way up here, I'm not hitting the graph at all. I'm still not hitting the graph when I'm looking up here. From 0 on down, I'm hitting the graph. Only this region is hitting the graph, so only those values are on this graph. So since range describes the y values, those are the y values that are less than 0. So like I said, there's some patterns forming here. That is your exponential functions and graphing. To determine if something has exponential behavior, you should have a common ratio, which we call as the R value. Now, lines have a common difference. When we looked at a table of values and it was linear, we could count in a pattern like 5, 10, 15, 20, and we realized that the change was 5, and so your slope was 5. In exponential, it's not a common difference. It's not what you added or subtracted. It's what you multiply by. So what you do is you look to see, first of all, that you have an even increment. Make sure that your x values are counting in the even pattern, which in the first example, they're all going up by tens. That means I can compare the numbers to each other. So looking at the x value and just establishing that they continue a pattern, they count by 5s, they count by 10s, they count by 3s, allows us to look at every single term in this problem. So the x value doesn't have to do anything with the r value. It just tells us that we can compare the terms that are next to each other. So if I look at 25 and 10, if I divide 25 by 10, that tells me what we multiply by to get there. So 25 divided by 10 is 2.5. 25 divided by 10 is a 2.5. That tells me that we multiplied 10 by 2.5 to get to 25. So if I times this by 2.5, I get 25. Let's see if that pattern continues. So now take 25, multiply by 2.5, and we should get 62.5, which we do. And times that by 2.5, and you should get 156.25. So because that pattern stayed consistent, the common ratio of this, my R value is 2.5. Yes, it's exponential. Looking at number 2, let's figure out our R value if there is one. So again, you work backwards to establish it. 32 divided by 64 will establish what we think is our R value. So when you take 32 and divide it by 64, you get 0.5. So if I take 32 and times it by 0.5, I should get 16, which I do. Take half of 16, you get 8. Half of 8 is 4. Half of 4 is 2. So therefore, yes, it's exponential. and my R value, the common ratio, is 1/2 or 0.5. In example number 3 here, to figure out what our R value might be, we take the one term and divide it by the previous. 16 divided by 12. When you take 16 and divide it by 12, I get 1.33 repeating. So keep that on your calculator and times it by 16, and I do not get 20. When I take 1.3 repeating and times it by 16, I get 21.3 repeating. Does not work, not exponential. If it's not exponential, that's not even an R value. We don't know what that is. We don't care what that is. We're just saying it's not exponential. And actually, if you look, this is probably linear because the numbers are increasing by adding 4. 12 plus 4 is 16. Plus 4 is 20. Plus 4 is 24, 28, 32. So number 3 is not exponential. It's actually linear, but you won't have to decipher on your homework. All right, here is your lesson summary, and here's your practice problem. Good luck. I know it takes some time, and these were a little longer notes, but I think it'll be fine once we establish those patterns. Good luck.